product rule, you've learned the quotient rule, there's one more big one to learn, and it's called the chain rule. Now, before we learn the chain rule, let's evaluate this derivative using techniques we already know. I'm going to start by rewriting f of x. I'm going to expand x squared plus 1 to the third. Let me start by multiplying these two expressions. This would be x to the fourth plus 1x squared and 1x squared is 2x squared, and of course 1 times 1 is 1. Of course, x to the fourth times x squared is x to the sixth. X to the fourth times 1 is x to the fourth. 2x squared times x squared is 2x to the fourth, and 2x squared times 1 is 2x squared. And then finally, 1 times x squared is x squared, and 1 times 1 is 1. I think I have some like terms. X to the sixth doesn't have a like term, but 1x to the fourth and 2x to the fourth is 3x to the fourth, and then 2x squared and x squared is 3x squared, and finally, my plus 1. Now that I've rewritten f of x, getting this derivative should be simple. The derivative of x to the sixth is 6x to the 5, and the derivative of 3x to the fourth is 12x to the third. The derivative of 3x squared is 6x, and of course the derivative of 1 is 0. So f prime of x is 6x to the fifth plus 12x to the third plus 6x. Now, as I'm sure you can imagine, you wouldn't want to use that process if we were trying to get the derivative of x squared plus 1 to the power of 30, and that's why we need to learn the chain rule. Now, the chain rule is very similar to the power rule, so let's just quickly review how simple the power rule is. We use the power rule to get the derivative of something like x to the power of 3. Recall that when using the power rule, all you need to do is move the exponent into the front, and then just subtract 1 from the exponent. This would be 3x squared. We use the power rule when we have our variable x raised to a power. Well, we can use the chain rule when we have something a bit more complicated than x raised to a power. But it works pretty much the same way. We still take this power and move it into the front, and then we're going to subtract 1. So I'm going to write this whole expression raised to the power of 2. But there's one catch. Since this was a bit more complicated than just a variable of x, we must then multiply by the derivative of this piece, and the derivative of x squared plus 1 is 2x. I suppose I can neaten this up a bit. 3 times the 2x is 6x. And now let's take a second and see that this is indeed equivalent to this. Let me go ahead and square this x squared plus 1. So of course, x squared times x squared is x to the 4, and 1x squared and 1x squared is 2x squared, and 1 times 1 is 1. And I'm sure you can see, if you distribute this 6x, 6x times x to the 4 is 6x to the 5. 6x times 2x squared is 12x to the third, and of course 6x times 1 is 6x. In many situations, the chain rule can save us a ton of time. Like I said a few minutes ago, you would never want to approach getting the derivative to this by expanding this to the power of 30. But using the chain rule, well, it's a cinch. To get the derivative of x squared plus 1 to the power of 30, I need only move the 30 in the front, and then x squared plus 1 to the power of, I'll subtract 1 to the power of 29. But then I have to multiply it by the derivative of the inside. I can multiply 30 times 2x and say that the derivative is 60x times x squared plus 1 to the power of 29. Let's take a look at some more examples on how to use the chain rule. Here I'm asked to get the derivative of all of this to the power of 3. I'm going to move the 3 in front and subtract 1 from the power. But since this piece was more complicated than just a simple x, I must now multiply by the derivative of this piece. So I'll multiply by 3 minus 4x. I don't see any reason why we would square this. However, I suppose we can multiply the 3 times the 3 minus 4x. So I'm going to say my derivative is 9 minus 12x times 3x minus 2x squared to the power of 2. And just to be clear, when you learned the power rule, you were already doing the chain rule, you just didn't know it yet. To get the derivative of x to the power of 3, you put the 3 in the front, it became x squared, and then you were multiplying by the derivative of just a simple x, and the derivative of x, of course, is 1. The first thing I want to do in example number 2 is rewrite it. Recall that the cube root of something means that that is being raised to the power of 1/3. This x squared minus 1 to the power of 2 is being raised to the 1/3. And when I have a power to another power, I simply multiply those powers. So I'm going to rewrite this as x squared minus 1 to the 2/3. And now I can apply the chain rule. I'll move the 2/3 in the front. I'll subtract 1 from this, but then I need to multiply by the derivative of this piece. So this is going to be 2/3 times x squared minus 1. And if I subtract 1 from 2/3, 2/3 minus 3/3 is negative 1/3. And then I'll multiply by the derivative of this piece, which is 2x. I don't see any addition, I don't see any subtraction, I just see something times something times something, and I have a fraction and a negative exponent. I should be able to write this as one fraction with no negative exponents. This 2 is going to go in the numerator, this 3 is going to go in the denominator. This x squared minus 1 piece will go in the denominator because it has a negative exponent. I'm going to write x squared minus 1 to the 1/3 in the denominator. And this 2x belongs in the numerator. Of course, 2 times 2x is 4x. So my derivative is 4x over 3 times x squared minus 1 to the 1/3. Now here's a function that we could differentiate using the quotient rule, but let me show you that it's much easier to tackle this with the chain rule. Let me start by rewriting g of t. I simply moved the 2t minus 3 up to the numerator and changed its exponent to negative. I'm hoping you see that these are equivalent. Now let me point out that I would not need to use the product rule here because I simply have a constant multiplier. I can get the derivative of this the exact same way I would get the derivative of this. So to get g prime of t, I'll move my negative 2 into the front, and negative 2 times negative 7 is positive 14, and then 2t minus 3, I'll subtract 1 from this. Negative 2 minus 1 is negative 3, and then the only catch is I need to multiply by the derivative of this piece because this is just a bit more complicated than x, and the derivative of this piece is 2. I have a negative exponent, so I should be able to express my answer as a fraction. 14 and 2 will stay in the numerator, that's 28, and this 2t minus 3 will go in the denominator because it has a negative exponent. I'll make it 28 over 2t minus 3 to the 3rd. All right, it's time to get serious. Let me begin number 4 by rewriting it. I'm going to write this radical 1 minus x squared as 1 minus x squared to the 1/2. And I can't distribute this x squared because of this exponent of 1/2. So I'm going to have to approach this one using the product rule. So my derivative is the first times the derivative of the second, and the derivative of this, I'll need to use the chain rule. Ignore this x squared, and the derivative of this piece, we'll put the 1/2 in the front, and then we'll subtract 1. And then we need to multiply by the derivative of this, which would be negative 2x. So I have the first times the derivative of the second, plus the second, which is 1 minus x squared to the 1/2, times the derivative of the first, and the derivative of the first piece is 2x. Let me highlight that addition symbol. Notice over here, we have something times something times something times something, and over here, we have something times something. So I should be able to express this as one fraction, and I should be able to express this as one fraction. My 1 is going to go in the numerator, my 2 is going to go in the denominator, my x squared is going to go in the numerator. This piece has a negative exponent, so that piece is going to go in the denominator, and then my negative 2x I'll put times negative 2x also has to go in the numerator. I suppose 1x squared times negative 2x is negative 2x cubed. Over here, I'm going to write a fraction as well. Now the 1 minus x squared to the 1/2 belongs in the numerator, the 2x belongs in the numerator. I think I'll put the 2x first. 2x times 1 minus x squared to the 1/2, I'll put all of that over 1. Perhaps over here you notice that the numerator has a 2 and the denominator has a 2. Well, we're allowed to cancel those out because I don't see any addition or subtraction in the numerator, and I really don't see any addition or subtraction in the denominator. I see 2 times something to the 1/2, and up here I see negative 2 times x to the 3rd. So it's legal to cross these 2's out. I have a fraction plus a fraction, so I'll use the McFarland method for adding fractions. My denominator is this times 1, so my denominator is right here. And for my numerator, well, 1 times negative x to the third is negative x to the third. Then I'll put my addition symbol, and I need to multiply this piece times this piece. I have something times something times something. So this 2x is going to come along, but then 1 minus x squared to the 1/2 times 1 minus x squared to the 1/2 would be 1 minus x squared to the power of 1. In the numerator, I can distribute this positive 2x. Positive 2x times 1 is positive 2x, and positive 2x times negative x squared is negative 2x cubed. Finally, my negative x cubed can combine with my negative 2x cubed to make negative 3x cubed. Then, of course, the plus 2x. And that's all over the 1 minus x squared to the 1/2, which I can express as the square root of 1 minus x squared.